Okay, so I'm basically going to look at all possible locations I might be in one step from now. You know? And looking at this expectation, you know, given that I started there. What's that? I'm not done. Hold on. I'm not done yet. Wait. All right, so I'm looking at all possible values I can be at time 1. And so I've got, hold on a second. Let me write it down and then we'll stare at it. So what's your question?
Not sure now.
X1 equal to X prime.
I'm trying to absorb it all.
Yeah. No, I know. I'll slow down. So this was a definition, really. I mean, I just went and decomposed it a bit. And then I'm saying that x of 1, you know, given I started at x, it can take on various values with that probability. You know, x prime is a value, possible values of x of 1.
I think maybe we were expecting to see the PU times the cost.
Yeah, that's
PU
what I was
times
It's right there, the cost. No, it's same there. Oh, I just brought it down.
No,
This and this are identical.
Another expected value.
Yeah.
But I think.
Oh, it definitely has to be.
I thought the expected value was the probability function.
Well, the only thing I wish I had done is I wish I had swapped out the sum over time here, but I'll do that in a minute.
Why isn't it not just the PU times the cost function as opposed to? I thought the expected value was defined as.
This is just a one-step transition matrix. I mean, right here, I'm looking at the expectation starting at x of 0 equals x, all right? And all I'm doing is I'm saying, well, that expectation, I can look at the expectation given that I started, that at time 1 I'm at x prime. But I have to look at all possible values of x prime and sum over the probability of being there. That's all. Yeah. You know, there's an expectation at time t, so is this. I'm just breaking it down. All right. But I really want to swap out that sum and min. So this guy's adapted. So whatever x prime that is, it has to depend on it. So I can take this whole thing out. I can swap everything out. I can do anything. Oh, wait. Let's do this carefully. Hold on. I almost slipped up.
Pull the sum of P.
Oh, it's something. Yeah, that's right. So it's the sum over x prime. In fact, I'm going to take a beta out. I'm going to take one of these betas out. Let me make that beta t minus 1. I've got my notes there, but it's good for me to slow down, and it's also good for you to guess what I'm about to do. What's that?
I think you're going to write.
Oh, I'm definitely going to write min. I need that min. Oh, I'll do it for you.
Thank you. That's all
Well, it's also good for you to guess what I'm going to do and then do it. But I've got the sum. I've got that. Well, I'll keep it as 1.
Hold on. What happened with the beta?
Hmm?
Oh, you just took out 1.
And now we stare at that. And remember about this time homogeneity, okay? Basically, the dynamics don't change with time. So if I start at time 1 and look at the total cost to go, from x prime, it's the same as starting from 0 at the same state x prime. So what is this monster minimum? It's 8 star, beta, because that is it's going from 1 to infinity, so it's beta 0, beta 1, beta 2, so it's the right sequence of discount factors, and this is the cost, t minus 1 steps ahead, given I started x prime. So there you have it. All right.
What's DCOE?
Yeah, I was about to say it. So the discounted cost optimality equation. Okay. All right. And so there it is.
Optimality equation?
The optimality equation. So the discounted cost optimality equation. So this thing here is obtained by something that looks sort of like our Poisson equation, but it's got a discount factor beta there. Yeah, and a minimization.
How do you transition from x prime to x, like in the same part?
Well, right here, I mean, if you think about it, what is this expectation? It's the expectation t minus 1 steps in the future of the cost, given I started at x prime. Let's just start anew at 1. At time 1, I'm at x prime, and t minus 1 steps later, I'm looking at the expected cost. I'm multiplying that by beta to the t minus 1, and I'm summing from 1 to infinity. That's basically that definition. It really is. What was the question again?
So the reason is because there's a sum over x prime, but then you at that specific it's the matrix.
Yeah. So here's that compact notation I'm forcing you to. This whole monster is 8 star beta of x prime.
Yeah, that's what I mean. Because it was a sum identity.
So this whole crazy sum is just with the minimum. The whole thing in brackets is 8 star of x prime, but then I'm matrix vector multiplication. All right. Yeah. Okay. So there's the discounted cost optimality equation, and because there's a minimum, it makes it a bit hard to solve. But we've got a whole bunch of ways to solve it. So, yeah.
So that at the bottom there is 8 beta star of x prime.
No. Don't forget our notation. When I wrote it down, I'll write it down again. When I write down pu h of x, I mean the summation over x prime, pu x to x prime, h of x prime. Okay? So this is the thing I said, it was up here a moment ago. I'm going to make you, I'm forcing you to to use this because I don't want to have to keep on writing sums in situations like this. You know, it's really, really tedious. All right. And so you can imagine what happens in the stochastic case. I mean, the average cost case. What's that? I'm not going to derive it. You can go through the same arguments. You know, I wrote in that relative value function. It's the same equation almost. But any more questions on this derivation? You do need to know it. Not for this exam, but the next one. You don't need to know it for this coming exam, but you definitely need to understand this thing. All right. So we can take a guess at it. What will the average cost optimality equation be? I say it's the same thing. There's no beta though. So that relative value function that I wrote down before, you can go through and actually use the same set of arguments. I know it's a bit weirder looking because it's a random stopping time. I mean, here we didn't have that. Here we had a deterministic sum, and there we would have a random final time. But that was why I derived Poisson's equation with that representation. Okay, so I'm not going to do it in the controlled case. I showed you one representation of Poisson's equation in terms of an expected sum to a hitting time. You know, I'm not going to do it again. So using the exact same arguments, you can derive this equation for that relative value function I wrote down. It's a solution to this equation. And the reason there's an eta star there is if you subtract it over, you'll get the C tilde that I had before, C minus eta star. Yeah. All right, so it looks like Poisson's equation, and it is. If you plug in the minimizer, you'll get Poisson's equation for a particular policy. All right, so I was hoping to do that. Just blast you with it. Just here's a cost criterion, here's a model, and here are the two dynamic programming equations we'd have to solve. And you can imagine you can't do it very easily very often. We'll take a break in a second. I just want to say a couple of things. Where are we going to go with this? Okay, so this value iteration algorithm that we looked at last week, it applies to either one of these problems exactly the same. And the analysis of value iteration is identical almost to what I showed you before. Okay, you can even use coupling. So, and I might give you some high level, some parts of the theory, but I'm not going to go into a lot of depth. There's something called policy iteration. I'm not spelling that out now, we'll get into it later. That's a much faster algorithm, but it involves, I mean, each step is more complex. It's hard to compare the two. But this turns out, this is successive approximation. And this is what's called Newton-Raphson. And it's known that Newton-Raphson is damn fast compared to successive approximation for solving fixed point equations. That's what this is. And that's why you'll find this is just in 2 iterations you've solved it. But each iteration, it takes a lot of muscle. And this takes forever. And then there's an LP. what's remarkable is that these crazy fixed point equations are the duals of a linear program. It's wild. And that's another computational method. It's also an awesome analytical tool. It's just really, and it gives you generalizations as well. So suppose that I wanted to minimize the cost, but there's not just one cost, you know. You know, what's that? Linear program. So suppose I wanted to minimize some objective. I want to maximize my revenue, you know, but minimize deaths in the factory floor. And maybe the variance as well. I mean, you know, in real life, there's multiple objectives. In this formulation, you can do that. You can have multi-objective settings. You can have, you know, minimize one cost criterion subject constraints on others. You know, so it gives you. We'll get to that later. So, but that's if you really want to compute things exactly. In practice, we can approximate. I love this concept. Give me a value function. X squared, okay. Just give me some stupid function. And let's look at the discounted case. So this idea works for either of these problems. It's just a little easier to talk about this problem because there's this weird thing here that we don't know yet. So let's just look at this for a moment. So I'm going to look at the error, this minus this. And that's called the Bellman error. Why would I do this? H is a value function. H is a discounted cost optimal value function. It was just some stupid thing that Joel came up with. I don't know why you came up with X squared. But it's an optimal value function. For which cost function? What? You know, H solves a discounted cost optimality equation, but with a new cost function.
It goes to 0.
Well, check it out. Oh, I forgot the minimum. Sorry. No, I have to have the min. There's only a function of x. Sorry. Well, hint, take this b of x and bring it inside, you know, and I get 0 equals blah. That's exactly the same as this. I could always bring this over to the other side and say 0 equals this. So what's the new cost function?
C minus B.
No, C plus B. Yeah, that's why I was careful to put the minus sign on this side and all that. But the thing is that, you know, basically you come with a hack, you can easily, you can see why it's called inverse dynamic programming, because here we're given C and we want to find H, and here we're given H and we want to find C. You know? But basically, you know, your boss gives you a problem and you say, what the hell, I'll just try this hack. You come to her and you say, I solved the optimal solution, and I've got an even better cost function. Isn't it nice? Your cost function was linear in x. mine is quadratic, so I'm penalizing large x is better. So my cost function's better, and I solve the optimality equations.
How will you know the cost function better? Isn't it just going to be some random thing?
That's the beauty. You choose an h, so you get a reasonable cost function.
But doesn't that require trial and error?
Well, you have to get some intuition, and that's why in the second hour I want to show you an example where you can get intuition. Yeah, and yeah. All right. So yeah.
Now, I don't understand what you mean like by a better cost function.
I'm joking, but it might be I was saying before, cost functions aren't, they're a little bit arbitrary, and if this thing isn't a big distortion of the cost function, it better be non-negative. It better not make this thing negative. If you're talking about cost, it better have some nice properties.
Better in what sense?
It might be. Well, it might really be better in some sense. You say, well, you forgot you were only looking at a linear function of x. You're ignoring variance. So if this was a small quadratic term, maybe it's better. What the hell? It's just. I mean, it's problem solved.
So made a solution using that cost function to give you more insight?
No. It's a solution. I'm saying I'm optimal with this new cost function, and if I can convince my boss that this is a better cost function, I get a raise. And in practice, we're going to show that these things are stabilizing provided C blows up, and as long as the sum still blows up, my policy will still be stabilizing. And if we're, I mean, if we have a computation, that's only for finite state spaces. If we're looking at a large state space, I really care about stability. And so as long as this still has a nice property that it blows up off of bounded sets, I'll still have a stabilizing policy, and everything will be good.
So I'm still on the same topic.
Yeah.
Help me to escape this circular logic that I'm experiencing. I thought that you use the cost function to define how good you are.
That's right. So given a cost function, I compute a policy. That's often very hard. So what's called inverse dynamic programming is out of your own genius, you choose an h for which this new cost function is still good. Maybe not better, but it's still good. And you've solved an optimal control problem with a cost function that's easy to sell to your boss.
Okay. Oh, that is close enough to...
Yeah, one thing is, I mean, this is small, for example. Yeah, that's right. Yeah. And, yeah. Should we take a break? Okay. So I think I'll only be able to start at the ends of the course. When we do Q learning and TD learning, all of that, it's all about, in a way, trying to make that Bellman error small. So you have a parameterized family of candidate functions H, and you want to choose the function in that class that has, say, minimum Bellman error or something like that. So it's sort of think of it as a way of evaluating an approximation. All right. So here's an example, that was brought to me 10 years ago, I guess. God damn, time flies. Yep. Just thinking. So. Okay, so Intel was spending a lot of money on this 15 years ago, how to decide on trade-offs between energy consumption and delay. And basically on a mobile computing device, I don't want to burn up, they obviously haven't solved it, because my God, it's terrible how these computers work. They're doing nothing and they're just heating up. I don't understand it. But anyway, basically, if you're using very little energy, there's going to be buffers are going to fill up. There's going to be big delays, and so you crank up the energy and clear those buffers. How should you adjust the energy use as a function of buffer size? Okay. So basically, it's like an MM1Q. Is the model they looked at. Okay, so it's just like a queue, except let's assume that so there's a buffer here, and let's just say that I kill off one packet per time slot. You know, if U is 1, I knock out one packet. If it's 2, 2 packets, and so forth. And then in each time slot, there's an arrival of new jobs to this buffer. Okay, so AFT is not 0, 1 like before. It could take on, it could be 10 million. It could be any. If it's non-negative, let's assume it's integer valued. You know. So X of t and U of t both evolve on the non-negative orthant. But obviously then there's a constraint, because if U is enormous, it could make the state negative. So in here, there are often state constraints as well. All right? So in this case, we always have U of t is less than or equal to X of t. You're basically saying, I don't know what this is yet. I'm going to knock those guys out possibly. And so we've got a model. We're going to make that IID even if it's not. That's a modeling choice. If you said there was memory in the arrival stream, you'd have to make this model more complicated, right? And we need a cost function, and I'll have notes for you with all sorts of different possibilities. We'll take a quadratic. And unfortunately, I used, I don't know why, I should have changed it. I'm going to change it right now. Anand, is he here? Yes, remind me to a place to use R for the weighting constant in front of U squared. All right, because there's something crazy in the notes. So the reason for the X there is that they're making the assumption that the cost of delay is a linear function of, the cost of delay is linear in the length. Now, like I was saying, if I put in X plus 1/4 X squared, nobody would mind. That'd be a perfectly reasonable cost function as well. Having X is not sacred. That was my point before. YU squared, that is a model fitting. They basically, empirically found that that the energy is approximately the square of the processing speed. That's an approximation. Some people say, no, it's not, it's 3/2 or something, or it's linear and then 3/2. So there's all sorts of, but it's just sort of, anyway. So you see, again, that's not precise. You do some experiments, and you see, well, it's convex, and U squared's a pretty good fit. Right? And the main thing then is I've got a parameter here, and I can get a feeling of how the policy changes. I change that policy. Maybe the sensitivity is not that great. Okay. Now we can solve this practically with 2 replaced by anything greater than 1 in any R here. And by solve, I mean I'll give you an H, inverse dynamic programming. It'll be so perfect you wouldn't believe it, by using a bit of intuition, right? Now, that is a monster. Forget it. Let's work it out. Okay, so it's the minimum of this. Now remember, PU8 star, nothing's changed. When I hit a function by P, I mean a conditional expectation. So it's just this expectation of h one step in the future, which is right there. In fact, yeah, forget the x. The expectation of h of x minus u plus a. Is that it? And then I'm forgetting something. And then plus a to star. And there's a star missing. Anything else? Okay, so when I write P matrix vector multiplication, but that's usually the most valuable interpretation. You know, when I write PH, I still mean the conditional expectation of the function one step in the future, but now given that the current state is x and given the current input is u. And as you can see, that's why it's sort of like a matrix that has a lot of rows, you know, and then d columns. You know, and you can see why you're screwed. I mean, the thing is that packets evolve on the integers, yeah. I mean, and all that, but Jesus Christ. I mean, I don't want to treat this as an integer program. You know, I lose everything. You know, it's horrible. You know the structure here. When you look at this, you can't do it. So you can't do a thing. I mean, what would you do with this? You have no intuition. You're completely dead. All right. And so I was at a workshop in Caltech 10 years ago or something. God, 11 years. No, 10 years ago. And I saw a talk about this by Adam Weirman, who's a professor there still. And they had done numerical experiments. They had applied value iteration, and they found this. They found it was sort of concave looking, you know. So this is x, phi star of x. That's the optimal policy, okay? I mean, phi star. You know, I forgot to say that when you take the minimum, it would be clear from the proof that the minimizer gives you the optimal policy. When I write u star here, I mean the u that minimizes this. So they looked at this, and you can imagine, I don't know, you don't know me, but I went crazy when I saw this. I said, I can show you why that's true, you know. And they had conjectures that it was a root, like that phi star of x was like something like some x to the alpha for some alpha and things like that. Yeah, we won't be able to completely do it. But the main thing is calculus. Okay, so one of the most important concepts in control is somebody gives you a stupid model, you throw it away, and you look at something tractable. And in this case, this model is not tractable because this equation is just horrible. And we know linear dynamics, convex cost, there's got to be structure here. And when you suddenly make it into an integer optimization problem, you throw away all that convexity. So relax, convexify, get rid of noise, just forget about stochastics. And a fluid model would be, like I had before, is that I'd have like x, here I've got a difference, xt plus 1 minus xt goes down by ut up by a. So look at this this new thing instead. And what you'd like to do is minimize the total cost. I told you for the stochastic model, everything is total cost. Well, let's do the same thing here. So remember the HDB equations. So here's why I sort of remind you that up front, is that the HDB equation looks just like this. So instead of PU minus H, I have that DH. And I won't use that notation. I'll just say grad J star of X dotted with the dynamics minus U plus alpha. All right. And I claim that if I could solve that, then J star would be my H. And I have to convince you that's a good idea. So I'm not going to have time to show you how trivial it is to solve this. Well, at least actually I have to modify the problem a bit. Yeah. I mean, notice that in this model, if x of t eventually is going to get to 0, you know, or it'll get closer and closer to 0 anyway. That means that, I mean, if x of t is going to go to a stationary point 0, then u of t is going to have to be alpha for this fluid model. All right. So this cost function won't do, because if I'm driving the state to 0, then my cost just becomes alpha squared here, and so it becomes infinity. So I'll have to modify the cost slightly. Yeah. I'll have to, but let's not worry about that right now. I'll get to that. I'll explain how we modify the cost next lecture.
This can be like G star of X can be framed as whatever the minimization subject to as a constrained minimization problem, right? I mean.
Well, the thing is, yeah, this is some horrible infinite dimensional monster, but this function is solved by this simple, trivial thing, and we'll see if we can solve this on the back of an envelope.
Yeah, but like the grad J star of X looks like Lagrange.
No, it's a derivative. Oh, no, forget it. This is one-dimensional. Is this a ddx? Oh, I mean, no. ddx. Yeah.
No, I mean, I just...
No, it's nothing.
We are sort of... Seems like we are relaxing the constraint, the dynamics.
Yeah. Relax. That's what you do in control. Somebody tells you something's an integer problem, you tell them, screw you, I can convexify. I'll take a min or a max floor in the end. You know, sometimes that doesn't work. Most of the time it does. In this case, it just solves the problem. I mean, basically, once you understand this problem, you know, the stochastic problem solved. You know, completely. You know. And you should always do it in control. You should always look at especially if you can come up with a convex relaxation, do it. It's, you know.
Going way back, the ACOE isn't kind of circular because you need to know what H star is.
For what?
Compute.
No, there's two unknowns. So for the ACOE, there's two unknowns. H star. So it's in a d-dimensional state space. I mean, not d dimensions. In a state space of d elements. I need to know H star of X for each of those D elements. So there's a vector of size D. That's a scalar. So there's D plus 1 unknowns. But this is not unique. You know, so I can always fix the first element of H star to be 0, for example. So they're really D unknowns. You know?
Right.
Yeah.
But
so that's an unknown as well.
Right, but then H star appears in the formula.
No, it's a fixed point equation, and the unknowns are eta star and 8 star.
Okay.
Yeah, that's all. Yeah. No, it's.
Yeah, just that you can condition 8 star, like one element of 8 star.
Yeah, so the d unknowns. It's identical to Poisson's equation. Poisson's equation, it just didn't have a minimum, and it had 2 unknowns. I didn't know eta and I didn't know h. You know? Yeah. And there it was easier to first find eta and then find h, but you didn't need to. All right. So why would I do this? So what possible motivation could I have? Well, let's try our trick. You know, just to give you some intuition about how on earth can you justify this. Now, how does it fit with this? What we're going to find out is that this function is wonderfully smooth and convex and nice, and it is differentiable. It has, you know, we'll find a solution, and because of that, I can go through and do a Taylor series expansion. I'm going to, next lecture I'll show you it. It's just all it is. But
we're assuming that we have it now.
Turns out it's a constant times x to the 3 halves. And the constant we can compute as well. Nothing to it. It's in the back of an envelope. Yeah, it's just nothing. But the thing is, I do have to modify the cost a bit. I have to, instead of looking at where'd the costs go, instead of looking at u squared, I have to look at the deviation. You know what I mean? I have to look at, take that thing squared instead of u squared. So, you know, u minus its steady state value for this fluid model, which is, you know, nothing. It's a minor change to the model. Yeah. In fact, that is sort of important here. But if you look at this, I can do a Taylor series expansion. You know, this is equal to. Well, I'll keep the expectation outside. Or I'll just put an approximation symbol there. It's approximately equal to j star of x plus the gradient of j star of x. Of course, that's just d dx, okay? Times the difference, which is minus u plus a. And what is that? Oh, yeah, that's right. I should keep it the same as that, shouldn't I? If I'm forced to make that d dx, I should keep it the same there. What is that expectation?
It's all linear, so you just
It's exactly equal to j star of x plus that term. All right, so I can write down this Bellman error, you know, and what will I get? Oh, I forgot the, I only defined this in a discounted case. But let's just define this to be the Bellman, no, I'm sorry, J star. Let's define this to be the Bellman error in the other case. I just said that's approximately J star of X. What's it? Yeah, J star of X. All right, all I did is I plot PU. All right, that's what I said was same thing. What?
Is J a function of U?
No. Oh, I'm sorry. Yeah, I'm sorry. J is not. J is given by this function of the initial condition. It's a solution to this HGB equation. But then, I'm trying to say is why would I take H equals J star? And the whole motivation is Taylor series. You know, and I can get away with this because J is not too crazy. You know, if J was hyper exponential or something, I'd be in trouble. But it turns out that J is a simple polynomial. And so I can get away with the Taylor series expansion.
Because if J is a function of U,
Oh, it's not. No. It's not a function of U. It's given by, it's a solution to this equation. Okay, so these guys cancel out. And what do I get? And there's an approximation here. What's that? There you go. Yeah. That's an approximation, okay? It's not exact.
What is that 0?
Oh, right there. Oh! Forgot. That's the Bellman equation, so I forgot to write equals 0. Sorry. Testing you there. Yeah. Okay. Now that, you know, it's not going to be good. I mean, you know, I mean, we'll see. I mean, I'll show you next time. You know, it won't be perfect, but definitely good enough. And you get the right answer because the minimizer here is like a square root of X. You know, the minimizer U star here is equal to some other constant times the square root of U. You know? I mean, that looks like, I'll call it B2. There's a B over there. There's another constant times the square root of U when you work this out. And so, I mean, yeah. Yeah. All right. So but the biggest thing is just to show you how integers get in our way so much. It's so nice to have calculus and be able to make use of convexity and everything like this. You don't have these tools in discrete state space. You know, it's really yeah.
So U is not
Yeah.
a function of, U star is not a function of X.
Yes, it is. Oh God, I wrote U there. I'm sorry. I hear people outside. When you take this minimization, what you find is that U is that. I mean, yeah. I mean, roughly. I'll clarify this next lecture. Yeah. Yeah. Now, how would you know? I mean, you have to. Yeah. What? What's wrong? So I forgot the 0 here. That was the HGB equation.
That's fine.
Yeah.
I was following what I got from the Bellman error is 0.
Yeah, but it's an approximation because we use Taylor series. Yeah, because we threw away, you know, J is convex, and so we'd actually get a bound.
Which means that h of x is a good, h of x equal to j star x is like a good approximation.
Yeah,
It's fine, and that's a different B, right? Because we have like so many B's in here.
Yeah, it's a different b. That is a constant.
that's why I put a 2 there. It's another constant. I'll give you.
And then
numerical
So
example.
My question is, how do you go from Bellman error being approximately 0 to U star equals B2 times the square root of x?
No, just look. Remember, I told you that. J. We're going to find out that J is x to the 3 halves. You know, so therefore its gradient is the square root of x. It's just. I'll do it next time. Remember, use quadratic. All right, and this is linear in U. So it's just a matter of taking derivatives.
It's not supposed to be obvious from that.
No, we'll see that. But it is obvious. Just take derivatives. Now you got to remember what U is. Use quadratic. You know, C of xu is equal to x plus a constant times U squared. You know.
So, but is for this example where you're saying that's where you get the solution?
Yeah.
It's C of xu is equal to x plus RU squared.
Yeah. Way to go. Yeah, right there. That's C of xu. Yeah. Now it's not quite that because remember we have to modify C a little bit, so it won't be quite that. I'll explain next time. But it just shows how the value of the deterministic thinking, and you often can get away with murder like this. So you can, basically. The only way you're going to get bounds typically is by doing things like this, using calculus. You can have a smooth function and you can use Taylor series. It's the only hope. You can't even think about something like this where h is defined in integers. It's impossible to think about this.
So how does this result relate back to the original countable?
Well, no, the thing is that if the Bellman error is 0, well, I haven't given you a result for the average cost case. But we all agreed if the Bellman error were 0, we've solved the problem. And if it's approximately 0, then I can go to my boss and say, look, my cost function is almost the same as yours. Give me a raise. What?
You should get the zeros.
Well, no, I see what you mean. Oh, yeah. You're right. This is the solution to this equation. I'll take the floor. Yeah. And also, I'm going to have, this will not be feasible, maybe, so I'm going to have to do two things. I have to translate this to something I can use. One, I have to make sure it's integer valued, so I'll take a floor or ceiling. And two, remember U had to be less than X. And that wasn't true here. We had no constraints. So you have to take a min there as well and all that. Yeah. So the actual phi star of X. The actual phi star of X looks like a straight line at first. And then it looks just like a square root. And if you compare the fluid policy and the discrete policy after value iteration, you can barely see the difference. There's a tiny gap here. It's really amazing. So it's a great success story where things match up. All right, so we'll spend some more time on this example because it's useful to see something like this. Because you can learn. You can go to Wikipedia and learn what policy iteration is. On your own. I'm going to give you a bit of motivation more than anything. I don't expect you to memorize all these algorithms. I want you to understand what they come from. Yeah. All right. Until next time, and.